Hello everyone, thank you for coming to my PhD thesis defense mock presentation. My name is Zhongkan Ren. I'm a PhD candidate in Mechanical and Nuclear Engineering department. So today's topic is on the organosilicon polymer-derived ceramic fibers, fabrication and molecular structural investigation. This slide shows the overview for today's presentation. First of all, please allow me to go through a little bit of background information about myself. My name is Zhongkan Ren. I'm originally from Yantai, China, a very small fishing town. So, for my undergrad degree, I moved to a neighboring city, and then I obtained my bachelor in material chemistry degree. And after that, I came to the U.S. and I finished the master in mechanical engineering, but with the material science option. So, in order to continue the graduate level studies, so I joined K-State. I joined the Nano Material Lab in 2018. So because I have a very strong background in material science, and I had many experience working with ceramics in my undergrad years. So when I joined the lab, I chose the synthesis of polymer-derived ceramic fibers as my major research interest. However, when I got here, I found that this new type of ceramic was totally different from the ceramic I used to work with. So therefore, please allow me to go through a short literature review on this new type of ceramics in order for you to better understand about this new concept. And we have published two review articles on this topic. So if you want more information, you can look up there. First of all, ceramic is one of the oldest man-made material through heat treatment, and then a brief history of ceramic is shown in this slide. I have marked out some important moments of the ceramic as well. As we can see that ceramic already has 30 years of histories, and then but today we are still using the ceramic for the same purpose as the container. It's not changed for over 30,000 years, except we have found some more advanced application for it. However, if we look at the very first ceramic artifact, so the manufacturing of this artifact has not changed that much from now, because they started with this clay material and then they shaped it with their hand, and then they heat treated using the flames. Now, at these days, we have refined the raw material. We can use the powders, and then we can apply the faster and more accurate shaping technologies. We can also raise the temperature at even higher than just using the frame, or with the microwaves or IR radiations. However, the basic concept of the ceramics has never changed. It always starts with inorganic solid, and then we always have to heat treat it at very elevated temperatures. So however, for our new type of ceramics, which was found in 1960s, and then initially was named molecular ceramics, because the basic concept was totally different from this powder-based conventional ceramics. So instead of using powders of inorganic oxide or salts, the molecular ceramics often synthesized from organic compounds such as monomers or polymers. Therefore, the heat treatment requirements are very different. In order to slightly melt and then reshape the powders, especially the inorganic oxide powders, we often have to raise the temperature to about 1800 degrees Celsius. However, for our molecular ceramics, pyrolysis temperatures are only up to 1000 degrees Celsius, and this temperature is very enough to decompose all the organic components in the precursors and converts it to the ceramics. And then through these two different heat treatments, the resulting microstructures are also different. For powder ceramics, it's usually polycrystalline microstructure with ionic bonding in it. However, for our molecular ceramics, we can either achieve the amorphous or crystalline nanostructures with covalent ceramic generated. And then also this amorphous structure usually comes with this unique nanodomain structure. And this structure is known to be very helpful for the high temperature stability and then oxidation resistance. And then also one thing that is not achievable from powder ceramic is the ternary or quaternary system. These systems are usually thermodynamically not possible for the powder ceramics. So in this slide, a very detailed polymer dry ceramic synthesis technique is shown. So we usually start from polymers or oligomers that are available from the market. However, it's also possible to synthesize our own polymers from the monomers. And then also at this stage, at this polymer stage, we can apply many types of polymer shaping techniques to achieve whatever the shape we want. For example, we can achieve fibers or 2D coatings or even 3D printings at this stage. And after we achieve the shape, we have to heat it up to a moderated temperature to cross-link it into a three-dimensional network polymer. And this polymer becomes infeasible. Then in the later high temperature pyrolysis, the organic components get decomposed. However, inorganic components will leave behind and form this amorphous ceramics with the nanodomain structure. And then also during this pyrolysis, where the transition between organic and the inorganic happens. Now, if we keep increase the pyrolysis temperature, if we push this temperature behind 1400 degrees Celsius, and this nanodomain structure will start to degrade and then recrystallize into two separated phases. Now, another benefit using this polymer dry ceramic technique is that we are already given this large varieties of precursors, and then thanks to the innovation in polymer synthesis techniques, we can swap and add desired element into our polymer, our system. And then it's also possible to tweak the side groups of the polymer and then change the rheology of the whole precursor in order to meet our requirement. Now let us discuss a little bit about the PDC fibers. So very first, the silicon carbide fibers were synthesized in Japan and by Yajima's group in early 1970s. The Young's modulus of these fibers could reach 160 gigapascal. So this value is about 70% of carbon fibers properties, which means that this silicon carbide is already very comparable product to the carbon fibers. We have all witnessed the success of carbon fibers. It's now dominating the reinforcement field for all types of composites. Once it was also considered a luxury product due to the high cost. However, right now, thanks to the innovation in techniques, the carbon fiber price has gone down, and then it's very readily available in consumers market in a very affordable price. So why do we still want these PDC fibers if we cannot beat the carbon fiber in mechanical performance? So because there's one big limitation that carbon fiber cannot overcome is the application temperature. We know that the carbon fiber are not stable at a temperature above 500 degrees Celsius, and then the structure gets decomposed and the mechanical properties drops down dramatically. Therefore, we didn't have this alternative at the high temperature range until we found these PDC fibers, and then with the very comparable mechanical performance and also high temperature stability, oxidation stability, and then creep resistance at elevated temperature. So, which means this reinforcement, these fibers, can be a ideal reinforcement for high temperature application such as ceramic matrix composites. And one thing to mention is that the current manufacturing technologies are only available in Japan and Europe. There are several reasons why these ceramic fibers are extremely hard to make. So firstly, the spinning process has a very higher requirement for the morphologies of the precursors. We can either start from a solid polymer or liquid polymer, but in terms of solid polymer, it has to be either meltable at an elevated temperature at a moderated temperature or dissolvable into a solvent to form a liquid phase. And along with the liquid precursors, they all need to have a certain viscosity, a sufficient viscosity to meet the minimum requirement of spinning. And then even though we obtain the fiber form out of the polymers, these has to be also cross-linkable and into a solid infeasible solid phases. And these solid phases also has to be stable at elevated pyrolysis temperature and without much of shape changes during the shrinkage. And one more thing to consider for this ceramics is the cost effectiveness. As we know, the silicon carbide fibers are the overall best performing fibers. They are only manufactured in Japan and Germany. The one major reason is that the polycarbosilane, the precursor, are extremely expensive to be manufactured here in the US. Therefore, we are looking for a different combinations of elements, such as the SiCN or SiOC here, with a very comparable mechanical performance and also extremely low uh, in in price to be manufactured. Now I want to introduce our PIRE project to you. Our NSF PIRE on polymer derived ceramic fibers. We have our research object is that we want to be able to draw this next generation multi-component polymer derived ceramic fibers within SiCNO with the concern of the cost effectiveness. Of course, we have to firstly understand the structural and the structure and property relation in order to, in the future, to be able to tweak our performance and then to achieve better fiber performance. We have also uh, you have also invited over 20 world-class institutes and then national labs to participate in our project from 5 different countries. And then all different institutes are playing different roles in this collaboration. For example, UT Arlington, they're doing some computational analysis of PDC structures. In the UC Davis, they're working on the thermodynamics of PDCs. In Lehigh, they're performing high resolution surface analysis. And then UC Boulder, they are making CMCs. And then MIT help us to calculate the cost effectiveness. And then in France, they offer a very high resolution NMR and then specialist for the help. And then in Germany, they synthesize their own polymers. And then Italy, they're doing 3D printing of the ceramic polymers, of the CMCs. Now we have a very clear motivation for our PIRE project, that we want to draw fibers from for high temperature applications, and the current SiC fibers are very expensive. We have much cheaper fibers. And then the current manufacturing technique, for example, the melt spinning, it has a very long production line and a very high requirement for the operation. So it's not doable in our lab. So we need to come up with our own lab manufacturing. So our roles at KSU is for the first year we provide the ceramic fibers to other collaborators, and then for their own applications. In the first year, we did understood the structure and the property relation of this PDC from literature. And then the second year, we were able to draw fibers from the selected precursor by hand spinning. And third year, we moved over to electro spinning for mass production. For this precursor selection, we have selected the silicon oligomers. Here, the siloxanes and the silazines as our precursors. These were originally offered from one of our collaborators due to the following desired features. Firstly, elementally, they are very abundant on Earth, the silicon, nitrogen, carbon, and oxygen. They're very abundant. Therefore, the price are relatively cheaper, and then they are all commercially available in large quantity. They also have very low toxicity, which is very easy for us to work with. And then structurally, they also have very high silicon concentration. And then within a single oligomer molecules, we notice that they have 4 vinyl groups in it. And these 4 vinyl groups are all potential cross-linking sites. And then these TTCS, oh, right, we name those fibers as we name those precursors as the TTCS in short. So for these TTCS, we have the following chemical and the physical properties. So chemically, the TTCS siloxane is very stable chemically in organic solvent or aqueous environment, and then they're both cross-linkable by the peroxide or other catalyst. So when they cross-linking into a very hard solid. This is very desired. And then they convert to ceramic at low temperature, as low as 500 degrees Celsius. It starts to convert, and then it usually finishes the conversion around 800 degrees Celsius, and then low toxicity, as we mentioned. So for the physical properties, the TTCs are water-like liquid at room temperature. It's both transparent and then low viscosity, which is very not ideal for spinning because we know the water is not spinnable by itself. However, it has a low evaporation rate. It's very good for us. So we can work in an open air environment without any equipment. So let's talk about the sol-gel spinning first. Sol-gel spinning, as its name suggests, that we firstly have to convert our precursors into a sol-gel form. Then we can draw fibers out of this sol-gel using our hand or machine, whatever the way we want. So for this project, TTCSZ silazane was used as ceramic precursors, and then DCP was selected as the cross-linker of it. So we firstly tried to draw fibers directly from TTCSZ and the DCP system. However, as I said, the viscosity was very low. Then we tried to heat it up into a temperature that it might partially cross-link it, and then we wanted to find this intermediate state where provides a certain viscosity that we might able to draw fibers from. However, I found that this liquid to solid conversion of this type of ceramic precursors were performed within a second. So it suddenly becomes hard solid from the liquid. So we were not able to draw fibers directly from this system. And then we come up with a new idea that, so for carbon-based polymers, we know there are several polymers that can be easily spinnable, easily spin into fibers, such as in this project we use PAA as the spinning agent. So which means we firstly add PAA into the water because it's dissolvable in aqueous system. Then we achieve this sol-gel of the PAA first. Then we mix our TTCSZ into the PAA and try to embed our molecules into the PAA rigid environment. Then during the spinning, the fibers are mainly formed by the PAA. However, our molecules are already embedded in the PAA, and then during the cross-linking, PAA might start to decompose. However, our DCP will survive and then cross-link into the hard fibers. So it will replace the PAA in the future pyrolysis. In this slide, I've shown the very early stage hand spinning setup. So we had this setup, we have this sol-gel pool at the bottom of the stand, and then at the top we have these fiber collectors, and then we can then use the wooden stick because it's very sticky to the sol-gel of our precursor, so to initiate the fiber formation, and then we can attach these fibers to the fiber collector. Then the only thing we have to do is to rotate the fiber collectors, and the fibers will be pulled out of the sol-gel pool and then gets collected on the collectors. So there are several engineering parameters that can control this diameter of the fibers. For example, the height between the sol-gel pool and the collector, the distance, and then the viscosity of the sol-gel, and then also the pulling force and then rotating rate. They all affect the diameter of the fibers. You can imagine that if we increase the height, then the gravitational pull on the fibers will be increased. Therefore, the fibers might get thinner by the pulling. However, this technique has a limitation, that is, we are not able to obtain individual fibers from this technique, because as you can see, the fibers gets collected and then covers the previously collected fibers, so they are overlapping with each other, and then during the cross-linking they might also cross-link with each other and then not separable after the pyrolysis. Here are some camera pictures for it. So from the most left one, the raw fiber rolls, we can see the individual fibers very nicely. However, we cannot separate them after the cross-linking. So the cross-linked fiber rolls look like a bird nest, and then if we keep heat treat them, we pyrolyze them, and then they become something like a spider web. So the fiber gets melted and then get stick to each other, so we cannot distinguish them anymore. So for that, we have to come up with another new technique that can spin individual fibers. So this is the enhanced mechanism. So we enhance the manufacturing of hand spinning fibers. So we have, instead of using the fiber collectors, I have built this aluminum bolt, and then we draw individual single fibers using the metal tweezers directly from the sol-gel pool, and then the fiber will sit on the two walls of the aluminum bolt, and then it will hang there, and then during the cross-linking as well. So after we are done with the fiber pulling process, then we can put this whole aluminum bolt into the cross-linking oven, and then we heat them, and then we cross-link them on site. So this slide shows a very detailed process of the fiber synthesis. And then it has three major parts. First part is the solder preparation, and then the second part is the hand spinning, and third, of course, is the post process with the cross-linking and pyrolysis of the fibers. There are some camera pictures of hand-spun individual fibers, and then the fibers are very thin, even thinner than our human hair, so it's barely visible from the very first pictures. However, the second pictures, as it gets cross-linked, the color turns to yellow, so it's more obvious. And then the fibers are all collected into a bundle for the further pyrolysis. So after pyrolyzation, the fibers can be separated from each other. And then we can then, using the characterization techniques, to determine the microstructure within it. So this schematic shows the structure, the microstructure changes happening in the fibers. So for the raw fibers, we know that the fibers are generally formed by this linear PAA rigid environment, and then the TTCSZ molecules are embedded within this rigid environment, and then during the cross-linking, the molecules start to cross-link with each other, and then from the more hard solid, the PAA might start to get decomposed at this stage. However, since our TTCSZ is already a cross-link, so the major mechanical performance is already coming from this TTCSZ. So after pyrolysis at 800 degrees Celsius, the PAA is expected to be fully removed, and then might leave some carbon elements behind, and then this carbon will add up into the free carbon nanodomain structures, and then the whole fiber will convert into ceramic fibers. So here we comes with the question that what would be the cross-linking mechanism. Since we have used the peroxide as our cross-linker, we have a vinyl group presented in our structure. So with the peroxide, the vinyl group might experience the polymerization, the free radical polymerization. Or there's another theory, is that this vinyl group might be connected to the methyl group under peroxide. So in order to confirm that, we have performed a tremendous amount of the characterizations. So for characterization part, we have applied the following characterization technique for our fiber. So scanning electron microscopy, SEM, help us identify the surface features of the hand-spun fibers. The viscosity analysis help us understand what is the contribution of PAA to the viscosity. The Raman spectroscopy is very specific to carbon in the pyrolyzed ceramic fibers. We can understand the carbon bonding situation. So further turns from infrared spectroscopy, FTIR, help us identify the chemical group changes happening in the precursors and crosslink, and also pyrolyzed fibers. So NMR is also applied to understand the microstructure and the bonding information of our fibers. The TGA analysis is performed to test the thermal stability of our hand-spun fibers. In order to answer the previous questions, what was the cross-linking mechanism, and then what is the final overall microstructure in our hand-spun fibers, and then also what is the surface features of our fibers. So we had to, in order to answer these questions, we had to perform the characterization to the samples at different stages. So starting from the raw before the spinning, and then S-spun after spinning, and also cross-linked spun fibers, and also parallelized at 3 different temperatures. And also we have done some characterization on neat PAA and then neat TTCS to understand what is the contribution of PAA to not only the viscosity, also to the final microstructures. Firstly, in the SEM images, we can see that the fibers, uh, even though the fibers are varying in the diameters, however, within a single fiber, the diameter is very uniform, and the diameter distribution is controlled within 10 microns. And the average diameter here is about 6 and then 3.5 and then 5 microns respectively for the samples parallelized at 600 and 700 and 800 degrees Celsius. We may also notice a little bit of surface porosity on the fiber surface. So viscosity analysis is performed to the TTCS-PAA hybrid system and also neat liquid TTCSD system to investigate what was the improved viscosity that we can get. So we found there was a 200 times improved viscosity, and after the incorporation of the PAA, and then we can meet the minimum requirement for spinning. So Raman spectroscopy usually confirms the free carbon in the ceramic system. So the carbon D band and G band are the signature peaks of the carbon, where D band represents disordered carbon, which means it's mostly sp3 hybridized carbon, and G band usually means the graphitic carbon that is a more ordered sp2 hybridized carbon bonding situation. And then we have detected the free carbon structure from all our 600, 700, 800 samples. However, in 600 samples, the fluorescence covered a lot of signals already, because that we think that at 600 the polymer to ceramic conversion is not complete. That's the reason it has an organic component, so it shows a very strong fluorescence. And compared and 700 degrees Celsius compared to 600, it's already showing a very good signals from the carbon, which kind of suggests that the this whole ceramic polymer to ceramic conversion might finish at this temperature. FDIR help us understand the chemical group changes in the polymers and then cross-link and then also parallelized samples. Firstly, if we look at the PAA signals, so this PAA is the neat PAA, and then we did the PAA at room temperature, and also we did the PAA heat treated at 160 degrees Celsius in order to determine if the PAA is also participating into the cross-linking behavior. And we found that these two spectrums are almost identical, which suggests that the PAA does not get involved in the cross-linking process. And then let's come to the TTCS-ZPAA and then cross-linked one. So we can notice there are decreased signals from vinyl group and also from the methyl group. So this kind of suggests that the vinyl group might have been attached with the methyl group in for our precursors. And then in the figure B, for the pyrolyzed samples, we notice that as we increase the pyrolysis temperature, the silicon carbon bonding is decreasing, and then correspondingly silicon-oxygen bonding is increasing. And then we can also notice the disappearing of the vinyl group, suggesting that actually it's at 800 degrees Celsius, the conversion is completed. It's more completed. So XPS analysis is a surface technique that determines it can be performed in surface scan or high resolution scan. So surface scan usually provides the information of elemental composition at that surface. So we may see that at 700 degrees Celsius, the silicon content is very low, actually. But however, if we keep increase the pyrolysis temperature at 800, the silicon content becomes double of the one at 700. And then carbon gets decreased and then oxygen gets increased. So the high resolution scan can help us identify the bonding situation that is in the ceramics. So it shows relatively the same information as the FTIR, and that silicon, as we increase the temperature, silicon carbon bonding is decreasing, and the silicon oxygen bonding is replacing the silicon carbon bonding. So NMR technique reveals the microstructure of our ceramic components. So we know that silicon oxygen bonding is increasing. So what would be the microstructure then? So after this analysis, we know that the silicon is forming silicon tetrahedrons with four elements at on each corner to be attached to the silicon. It can either be oxygen or carbon. So in the low temperature, since we have more silicon carbon bonds, so the most of the microstructure is limited to silicon SiO3C. However, for the higher temperature pyrolysis at 800, the structure starts to shift towards SiO4, the pure silica tetrahedral structure. And then in the figure B, it shows at 600 we can still detect some signals from organic components. This also means that at 600 the polymer to ceramic conversion is not completed. So this NMR shows the difference between the pure TTCSZ and then TTCSZ PAA hybrid system, both pyrolyzed at 700 degrees Celsius. So if we look closely into this pure TTCSZ spectrum, this spectrum is actually very similar to the spectrum that obtained from 600 degrees Celsius sample from the previous slide. So which kind of suggesting that the incorporation of PAA works similar to the increasing of the pyrolysis temperature for up to another level. So the carbon NMR also suggests the same thing, same information. For neat TTCSZ, we still can detect, even though we pyrolyze it at 700 degrees Celsius, we still can detect some organic components out of it. So in this NMR spectrum, what we obtained is the difference between raw and the cross-linked sample. So from raw sample, we may see that the signature peak is very sharp. This suggests the component is highly mobile. It has a high mobility. However, if we cross-link it at 160 degrees Celsius, we notice that there is a broad peak formed near the sharp peak. This broad peak means it's forming a rigid structure with a very low mobility, and then also decrease the sharp peak, suggesting the cross-linking is happening. And then the same information can be obtained from the carbon NMR as well. Here we can propose our cross-linking mechanism of our precursor. That is, the vinyl group is expected to be combined with a methyl group under the existence of peroxide. So since we think that some of the cross-linking is not completed, therefore it might have the following 4 different structures with the partially cross-linked one to fully cross-linked one. These 4 structures can all be existing in the microstructure of cross-linked samples. So TGA analysis determines the weight changes during the heat treatment. So we did the heat treatment up to 1000 degrees Celsius, and then we found that our pyrolyzed ceramic fibers is actually very stable in nitrogen environment. So it has a 96% of mass retention after the heat treatment. And then for a comparison, we did the cross-link sample TGA analysis also in the same environment. We found that we can notice that there's a uh, sharp mass drop around 400 to 600. So we believe this range, the polymer to ceramic conversion is happening rapidly. And then at about 800, we see this curve start to flatten out. So this indicates that the full ceramic to polymer to ceramic conversion is completed at this 800 degrees Celsius. And then PAA in air is done for the comparison that we provide. It suggests that PAA does not survive this high temperature pyrolysis. And then we have also provided our individual fibers to our collaborators at CU Boulder, and they are testing the strain changes during the heat treatment of the green fibers, which means these fibers are already cross-linked. However, they can still uh, increase the temperature and measure the length changes, and then determine what would be the strain changes under this uniaxial loading. So this content is not unpublished yet. So now I want to talk about the electrospinning section, and then we have submitted the manuscript to RSCL Advances, and then now it's accepted with the revision. We are also filing the international patent based on the electrospinning of ceramic fibers that we did, along with the K-State Research Foundation. So electrospinning is a very advanced and flexible technique with a very minimal setup, and then you can mass produce the polymer fibers. So it usually has this power source, high voltage power source, and then syringe and pump feeding system, and the fiber collector system. So as we apply the high voltage at the needle tip, the metallic needle tip, this charges will be formed at the surface of the sol gel. We're still using the sol gel or liquid. So it will be formed at the sol gel, and then this electromagnetic pulse will drag the fibers out of the syringe, and then it will form into the fibers, and then the solvent gets evaporated during this process, and then only leave solid fibers behind. So we can see the spinning process usually has these 2 different sections. The first one is called ohmic flow, where it's a very steady, it's a very stable flow out of the needle tip. And then after a certain point, it converts to this convection flow, which means it shoots to a random direction. And then because of we have this pulling force on our collector, so the fibers will get attracted and then collected on the fiber collectors. So the electrospinning process is actually a very complex electrohydrodynamic process. So it's very hard to simulate and then predict the behavior, the stability of it. However, if we only consider the ohmic flow, so we can simplify this model as a one-dimensional steady-state model, and we can draw the following three different equations from mass conservation, and then charge conservation, and then linear momentum balance. So the reason we want to look at the three equations is that we want to know what kind of parameters are actually controlling the stability of the electrospinning. So we can see that the mass flow and the internal force, and apply the voltage, the initial velocity are the factors that we can control. The radius of the jet is fixed because we were only able to buy the one type of metallic needle with the flat head. So therefore, we have built our electrospinning setup as the following, and then all the parameters are already optimized. There's a difference between, there's about 20 centimeter difference between the needle tip and the fiber collectors, and then the high voltage of 15 kilovolt is applied at the surface, at the needle tip. So the pulling force will drag the fibers out of the needle and then gets collected on the collectors. The solution feeding rate was about 3 to 5 milliliters per hour. And then all this, the syringe pump is controlled by this stepper motor. It's very high accurate, and then it's controlled by the Arduino control system. For this project, we have selected different precursors than previous hand spinning because we found that in the hand spinning, the nitrogen converts into toxic ammonia gas and then gets released during the spinning. So this is what we don't want to see. And then therefore we choose this more stable siloxane structures. So because we can work in the open air now. And for the comparison, and then to study the difference of to study the influence of the initial structure to the final microstructure. So we apply this 4 different types of precursors. For the second one, the platinum TTCS, is actually a complex of 4 TTCS and then platinum ions. And the platinum is used as the crosslinker for platinum TTCS, so we don't have to apply any DCPs for this sample. And this schematic shows the full full electrospinning process. It's very similar to our hand spinning, where we firstly have to prepare the sol gel, and then we can electrospin it, and then followed by the post-processing. The processing temperatures are the same as the hand spinning, but we were able to achieve this very large area electrospun fiber mats, and then we can cross-link them into a yellow colored cross-link the fiber mat. And after pyrolysis, you may see that the fiber mats are very complete without any warping. So in this video, we can see I can show you the ohmic flow and the convection flow, the changing point between that. So actually we can see a very thin line coming out of the needle tip, and then at a certain point it seems like it's converting to numbers of fibers. So this suggests that we have a very stable ohmic flow, and then the convection flow is also converting the liquid to a ceramic fibers. So for the characterization of the ceramic fiber mass, we choose very similar characterization techniques as the hand spin fibers. The purposes are almost the same. And then besides, we also included the nano indentation technique to test our mechanical properties of our fibers, and then the flame test as well. From the SEM images, now we can see that the electrospun fibers are very uniform in diameters. The diameter distributions are also very well controlled. The first row of the three figures are all from the same precursors, but they are row and then cross-linked and then parallelize the samples as the difference. So the fiber diameters are actually decreasing as we keep increase the heat treatment temperature. So as a result, we get approximately 1.5 average diameter for parallelized TTCS 40 TTCS sample, and then for the other three precursors, we are obtaining relatively very similar features of the fibers, and then the diameters are also very close, from 2.5 and 1.4, and then for DTDS is going down to 0.5 microns. So TEM and EDX is performed to show the same kind of information. We confirmed our diameter again, and also the EDX showed that in the platinum TTCS sample, we can still observe the platinum signals from it, which means the platinum is now embedded in our fibers. So we can also confirm that by these high resolution TEM images. So the black dots you see right now, those are the platinum nanoparticles. And then a close-up shot shows that the platinum nanoparticles has these crystalline structures. However, our PDC nanodomain structure does not show any repeating crystalline features because, as we mentioned, these are amorphous structures. So nanodomain, you may see the dark area and the brighter area. These are the repeating carbon and the silicon tetrahedron area. So Raman spectroscopy shows the same idea. So we can all detect the carbon signature peaks from our parallelized samples, but in the platinum TTCS sample, there's high fluorescence is made due to the existence of the platinum nanoparticles, so we were not able to obtain a very good signal. However, after background removing, we noticed that it has a very high amount of G band than the D band, which is suggesting in this sample it's more likely the sp2 hybridize the carbon bonding than sp3 hybridized one. So FTIR is showing is performed to determine the cross-linking behavior here. So pristine PVP is performed firstly to see that if the PVP also is participated in this cross-linking process. However, we think that the PVP are not contributing anything to the final structure rather than leaving some carbon behind. So for the comparison, we can notice that a signature peak at about 1050 for 4 TTCS platinum TTCS, and also the peaks from about 790 to 750. These signature peaks are all decreased, which indicating a very good cross-linking behavior out of it. And then in the final structure, we obtain we can see the silicon carbon bonding and then silicon oxygen bonding is presented. The XPS it's also performed to firstly determine the surface elemental composition, and then we can see that platinum TTCS sample provides the most silicon percentage here, the, the highest the silicon content. And then for the high resolution scan suggests that in platinum TTCS we have highest silicon oxygen bonding and the lowest silicon carbon bonding. For NMR spectroscopy is also performed to determine the cross-linking. However, in the platinum TTCS sample, we don't see a very obvious the rigid peak is formed after the cross-linking. So it's kind of very confusing for us. And then also the NMR spectrums from pyrolyzed samples shows the same information as the XPS presented, that in platinum TTCS sample, it's most likely the silicon oxygen bonding is presented rather than silicon carbon bondings. So nano indentation is performed on 4 TTCS samples. We try to embed this pyrolyzed sample in epoxy, in hard epoxy, and then we perform a indentation. We remove the surface layers, and then we rebuild this fiber features, and then we perform nano indentations on it. As a result, we got this fiber transverse modulus of about 5.7 gigapascal. For the comparison, for carbon fibers, it's about 8 gigapascal. So our fiber is actually also very comparable to the carbon fibers. The flame test shows the flame test is done to determine the thermal stability. This flame is the acetylene flame torch, and then our fiber mats are exposed to this flame torch in open air to determine which one provides the best thermal stability. As a result, you can notice that the platinum TTCS sample actually did not show any surface oxidation or warping or shape changes. However, in other samples, we can notice a slight surface oxidation, or in DTDS, we see it's completely shrunk into a small piece, and then the XPS surface scan analysis shows that before and shows the elemental composition before and after the heat treatment, and then we can see that for the first 3 samples, the 4 TTCS, platinum TTCS, and the 3 TTCS samples, the elemental compositions did almost not change. However, for DTDS, it is highly oxidized, and then carbon gets decomposed and then oxidized a lot. Here's a video clip for the platinum TTCS sample, and then we can see it's very stable even we are heat treating it. So no warping, no structural degradation, no thermal deflection. So in summary, we have produced ceramic fibers from this SiOC or SiCN system for the first time from cyclic oligomers, and the weight loading of the precursor to polymer was about 1.1 for hand spinning, and then 4 to 1 for electrospinning, which means we were able to apply 400% of precursors on our spinning agent. So then we were able to obtain this large area, 15 by 15 centimeter square electrospun fiber mass from our electrospinning setup. So the diameter of the fibers were about from 1 to 10 microns for hand spinning, and then 0.5 to 5 microns for electrospinning. And also electrospinning provided more narrower fiber diameter distribution, more stable. So fiber mass or closing by platinum had the highest silicon concentration, as well as a better thermal stability. I think they have some connections in between this silicon concentration and then better thermal stability. In conclusion, the cyclic pre-ceramic oligomers are unspinable. However, the fibers can be achieved by incorporating other linear polymers, and then the amount of polymers are very critical to the spinability of the precursor. So different precursors, or even with the very similar structures, so they produce very different PDCs in molecular structures. So different catalysts cause different cross-linking mechanism, and then ultimately affects the final composition and the microstructure of the processed ceramics. So for the future work, our electrospun fiber mass are being tested as a anode material for electrochemical energy storage devices, such as a battery or supercapacitor, by Shaquille, our own group member. And also the CMC production is going on by our undergrad students at KSU as well. So high resolution microscopic and the machine learning is performed at Lehigh. They're also using our fiber mass. And the mechanical testing of the fibers and the fiber mass needs to be done in the future in order to fully understand what's the structure and the property relation of the fiber and fiber mass. So synthesis of the pre-ceramic precursors can be achieved if we have this a student with a very strong background in chemistry and or chemical engineering. So here is briefly my research contribution to K-State or to the science. So we developed a social spinning technique for ceramic fibers. So I co-established this electrospinning setup with Davi, another our group member. Special thanks to Davi. And then we applied this setup for ceramic fiber production, and then it was very successful. And currently, we are providing this Sogel handspun fiber bundle to the CU boulder for them to be tested. And then we are also supporting our ceramic fiber mass to the Lehigh. And I'm also mentoring 2 undergraduate students currently and 1 in the past. So there were also 3 companies that showed a very high interest to our ceramic fiber mass. So we provided our ceramic fiber mass to GE, Honeywell, and the United Technologies. So here is my list of publication. Overall, I have 3 journal articles, and then 1 is accepted with the revision right now, and then 3 review articles with 1 book chapter, and then I have several conference presentation with poster presentations. So special acknowledgement to the NSF funding. We are very grateful for the NSF funding, and then thanks to my advisor, Professor Gurpreet Singh, for the help during these 3 years of PhD studies, and then thanks to the committee members. Thank you, and any questions?